All right, so welcome back to the second part of the Chapter 6 lecture. I apologize for the delay in posting this. I had actually recorded this the day before, but then when I went back to listen to the recording, all I could hear was my daughter just wailing in the background for like half the video. And I don't think anyone else listens to that. I'm going to try to learn physics. So I'm re-recording it Friday morning, and all right, let's just get into it. All right, so one of the things that we talked about in the previous lecture was this idea of energy transformation, which is sort of the conceptual way we approach these problems. Once you can identify the energy transformation and the conceptual things going on in the problem, that allows you to move on to set up the equations and mathematics behind this. So when you think about this question here, remember what you're considering for an energy transfer is what is on the left side of the energy transfer is where the energy comes from. And so it could either be a decrease in some state of the system, energy state of the system, or it could be the input of energy as a result of work or something like that. What appears on the right-hand side of the energy transformation is where that energy goes to. So something increases, right? So think about this question here. And the answer is A. Okay, so what's happening here is when you are pulling up the skier at a constant speed, we can see that their gravitational potential energy will increase because they're going to a higher elevation. And the energy comes from somewhere. It's got to come from work being done. So there's the rope is doing work, force times distance, right, on the skier. The constant speed aspect to this is important because that means there is no energy transformation involved with K. K doesn't change at any point here, the kinetic energy, so we wouldn't want to include that in our energy transformation. All right, so this question here is sort of a review of what we talked about for work last time. Remember, work is force times distance times the cosine of the angle between the force and the displacement vector, right? So look at this question here. Think about what the answer might be. The answer here is D. Okay, so let's look at C first. C has the force and the displacement in the same direction. So for that, the angle is 0 degrees between those two vectors. So we have positive work being done there. That force is going to be responsible to some extent for the displacement of the object. For A and B, we have our force opposite of the displacement of the object. So, the angle that you would state here would be some sort of obtuse angle. And the cosine is negative in the second quadrant. So mathematically, that's why you have a negative work here. But the conceptual understanding in this is that whatever force is being applied here, it's attempting to reduce the overall energy of the system. This would be like a frictional force of some kind that is acting on the object as it moves in the other direction. So that's probably what's going on here. But if this force acted alone, this would be decreasing the overall energy of our system. All right. So let's jump right into a problem. This lecture has a lot of examples. We are trying to utilize the concept of work to determine how the energy state of the system goes. So this is, I don't know if I mentioned this in the previous lecture, but what we're doing here is a segue. We've gone from forces and we're transitioning into energy, and the idea of work kind of bridges those two concepts up, because when we do work problems, we still need to make free body diagrams. We still need to be aware of all the forces that act on the object. We have to compute work for all of the forces that act on the object. And what you're going to see a little bit later in the lecture here is when we calculate all of the work that's being done by the forces, we can relate that to how the motion of the object changes. All right. So let's jump to the example here, which is right here. All right. So we got these two ropes that pull up into the sides. On this piano, we got gravity going down. So we're trying to figure out how much work is done by each of the three forces. All right, so for every force, what you're trying to do is you're trying to get three things. You're trying to get what's the magnitude of the force, what is the displacement that occurs while the force is being applied, and what is the cosine of the angle between the force and the tension vector, or what force vector, right? Okay, now the way I like to approach these kind of problems is to, identify for these forces if our work is positive or negative, and I like to manually put the negative or positive signs in my expressions, and I like to keep my angles acute angles. So when you're trying to figure out the angle between the force vector and the displacement vector, you look for an acute angle between them. So that means we're looking at either a parallel or anti-parallel situation of the vectors. So that's what I've done here. We have three forces. We have our tensions, and we have gravity. We are going down, so displacement's downward. That means gravity will be positive work, and the tensions are going to be negative work. Now, these tensions have x and y components. I don't need to consider any of the x components of these tensions because they are going to be perpendicular to the displacement, and automatically those components, they don't do any work. This is sort of why we have our cosine factor here, because we're only considering the component of force along the direction of motion. Okay, anyway, so I got my tensions, the work done by tension. So I got a negative sign, I got the tension value, I have the displacement, and I have a cosine 30 and a cosine 45. The 60-degree angle that you see in the figure here, we're looking at the complement because we're looking at how that angle is matching up with a vertical line, because the vertical line is the displacement, right? So we don't want the 60-degree or the 45-degree angle, we want the complements of those. So 30 degrees, 45 degrees, we're going to use there, and so we have values for those works. And then, of course, we have our gravity. The force of gravity is mg. We have our displacement. There's no angle between the displacement and the gravity vector, so we can straight out calculate the work for those. Now, I did an additional thing in this problem. I decided to sum all that work and to see what the net work is, because when you look at all the forces in the object and you add up all the works that's being done to get a network, that network is basically going to tell you what is going on with the system. So if your network comes up to 0, that means you're not adding energy to the system or taking away. So that means constant speed, right? If there's any net work, when we take into account all the forces, that can either increase or decrease the overall kinetic energy. If it's 0, there's no change in kinetic energy. If we had positive network, the kinetic energy would be increasing, and if we had negative work, it would be decreasing the kinetic energy of the system. So this particular case here, we're lowering this piano, and it is moving at a constant speed, apparently. Okay. Fantastic. Moving right along. All right, so that problem sort of leads into what I just discussed here. The principle that we're going to be thinking about here is what's known as the work-kinetic energy theorem. And what it says is that if you look at a problem and you analyze all the forces that are exerted on your system and you compute work for all those forces, you add it all up, you get what we call the net work. And that net work will be equal to the change in the particle's kinetic energy. Okay, so in some ways this is sort of similar to Newton's second law. In Newton's second law, we're summing all the forces up. We want a net force, and that will be equal to the object's mass times acceleration. So we're getting a sense of motion there. The kinetic energy theorem is sort of packaged in that a little differently, so that we can look specifically at the kinetic energy and therefore the velocity of the object. So that's kind of the reason we had developed all that stuff in the last lecture, to figure out different kinds of energy, to figure out the amount of work that's being done. on the system, ultimately we're trying to get to this point here. This is a pretty good way to solve a lot of problems. Very similar to force problems, honestly, but again, this is a segue into a complete energy treatment, which we're going to develop in the next chapter. We're not quite there yet. We're I mean, I introduced all these concepts of energy, but for now, we're just really focused on the kinetic energy, and we're not really considering any potential energies right now. Okay, so all right, so this is a great example that incorporates all these things we've been talking about so far and in the previous lecture. So let's go and look at this example. Here we go. All right. So we got a 1,000-kilogram elevator. We're going up, accelerating, right? At 1 meter per second squared for 10 meters starting from rest. Let's go through each part here. We want to know how much work does gravity do in the elevator, right? Actually, before I really get into those things, one of the things I'm going to need to do, and again, when you're doing work kinetic energy problems, not just energy problems, just work kinetic energy problems, or anything that involves a work, you still really want to approach this in the same way we approached our force problems. You really want to look at a free body diagram and write out Newton's second law, just so you get a good sense of how things look and what the numbers ought to be. Because part B is asking for how much work does tension do, and obviously we would need to know the magnitude of the tension in order to do that. So we have to figure that out. And you see the work is done on the left there. Tension's up, gravity's down. The upward vector for tension's a little bit bigger because we are accelerating upward. So my Newton's second law is tension minus mg equals ma, and from that we can get our tension. And again, you can see the work that's done there. All right, so let's just go through each part here. We want to know how much work gravity does in the elevator. Okay, now the elevator goes up, gravity points down. That is negative work. So the force of gravity is mg. So I got my 1,000 and my 9.8. My displacement's 10. The cosine of the angle, well, the angle is 0, right? That's the idea. You could say it's 180, and then you don't put the negative in the front. I don't like to do that. I like to be more consistent, and I like to always manually put in our negative signs and worry about acute angles. And that's just based on my experience teaching this stuff for years and years. I just see that students will mess up things more often if they are trying to put acute angles, because you can't always, if you try to put obtuse angles in there, because it's not a very consistent way to do things. Some problems, you can't do that at all. You can't put obtuse angles in. So, why not just be consistent and manually put in negative signs if you need them and make everything an acute angle, okay? All right, so we got our work for gravity. It is negative 98,000 joules. Let's look at what the tension's doing. We figured out the magnitude of tension, right? It's 1,000 times 10.8 because we add in that 1 meter per second squared for the acceleration. And again, tension's up and displacement's up, so the angle's 0. And we get a slightly larger work than we did from part A. We get 108,000 joules. So if we sum that up, right, our net work is, 10,000 joules. So what the work-kinetic energy theorem states is that if we have truly accounted for all the forces that act on this object and determine their work, whatever the net work is going to help us determine what the kinetic energy and therefore what the speed of the object is. Okay, so we're saying our 10,000 joules is equal to delta K. Delta K being final kinetic energy minus initial kinetic energy. Now we start at rest, so there is no initial kinetic energy, so we can just basically set 10,000 equal to 1 FmV squared, solve for V, we get 4.4 meters per second. Okay. Now, what I did is I did a little calculation at the upper right here. It's not really part of this problem, but I just showed through kinematics how we can verify that this is the case as well. Now, you may look at that and say, well, why don't I just do kinematics? It's so much easier. Okay, well, maybe for this problem it is, but it won't be for other problems. All right, so I'm just showing you the two methods here that we have. By the way, that will be sort of a strategy as we move on in physics here. You're going to learn all these tools, forces, kinematics, energy, momentum, all these different, ways to characterize the system and solve for things, and it's not always going to be clear which approach you ought to take. Some approaches are much easier. Some approaches are a ton of extra work. One of the things you'll see here, well, actually, you don't need to hear that right now. I'll tell you later. Okay, let's go. All right. So now, what we've been doing so far is constant forces. Okay, because constant forces allow you to calculate work much easier. I mean, the original definition we had for work is technically a line integral. And you do need to be considerate of how the force changes over the path that the particle takes. Well, if everything's a constant, you don't got to worry about that. You can take it out of the integration, and then you just got this nice F delta R cosine theta statement. Okay? But there are situations where you are going to have a variable force, and if your variable force has a very clear mathematical description, then you can perform the integration. But we do it like we did back in kinematics, in that we simply look at the graph and we work out what the area is bounded by the graph, and that will be our integration. So we're not really doing any, what's the word for that? Well, we're not integrating any functions. We're just conceptually working out areas, right? But that way. All right, so in this example here, we have a car that's being accelerated from rest. It starts off with a force of 5,000 newtons, and then as it moves from 0 to 200 meters, we see that the force will decrease. Now, obviously, this is going to be increasing the kinetic energy of this, but the way we'd have to figure it out is you'd have to work out what the what the area is here. So let's look at that. Okay, so first thing first is, what is this area here, right? So it's a triangle, so it's 1/2 base times height, and the base is 200, and the height is 5,000 newtons. So that's a newton meter, that's a joule. We have 500,000 joules that has been added to the car's energy in the form of kinetic energy. And now we just use our work-kinetic energy theorem. We do the same thing like we did in the other problem, where that 500,000 is equal to delta K, which is the final kinetic energy minus the initial kinetic energy. So 500,000 equals 1/2 mv squared. Solve for v, you get 26 meters per second. All right? So real straightforward. We don't have many of these kind of problems. If you do deal with the variable force, it will always have a very nice mathematical description so that you can perform the graphical integration very easily. So, but I have to just put that out there because it does show up in problems that we do. Moving right along. All right. So now we can start to look at energy models here. Okay. So again, this is what I've mentioned here, is now we're slowly starting to move in to pure energy concepts. And when we do that, we are thinking about our system's total energy state. And so up to this point, what you've learned about is kinetic energy, potential energy, thermal energy. The combination of the kinetic and the potential energies is what we commonly refer to in physics as the mechanical energy of the system. It's the sum of kinetic and all the potentials. When you incorporate a thermal, so what you're doing is you're incorporating any energy that was maybe dissipated to the environment, or maybe even to part of the system, but it's just not in the same form as kinetic or potential energy. We just refer to that as just sort of the total system energy. Now, the way that these problems are going to work is we have our system and we have our environment. And if you just consider the system, your change in energy is going to be 0, okay? Because energy is transferred between things in the system. And so there's no input or output of energy overall. If work is done on the system externally by the environment, then the E-sys changes. And so the sum of all these things will be equal to whatever the work is. Now, if the work is positive, then we're increasing the energy of the system, and if it's negative, we're decreasing the energy of the system. So you want to think about this as sort of bookkeeping the system, right? You're trying to characterize at one instance in time, what the energy of the system is, and you look at a second point in time, and you say, okay, what is the energy of the system here? And you see what has happened in between these 2 points, and you determine if the work has been done or not, and then you can solve your problems from there, right? So you'll see this a lot more as we move on, especially in the next chapter. This plays a much larger role, all right? So let's get into another example. This one's a little more complicated application of the work-kinetic energy theorem. Nevertheless, super fun. So let's get into this. All right, we got Susan and brother Paul. Okay, because it's a work-kinetic energy theorem problem, the first thing you ought to do is your free body diagram. I've made the assumption here that this baby is being pulled to the right, okay? So we have a normal force up, we have a gravity down, we have a tension that's up at this 30-degree angle, so there are X and Y components to the tension. We got a kinetic friction going to the left, right? And I will need to know, well, I know my gravity, right? And I know my tension. I don't know my normal force, and I don't know the kinetic friction, although if I get my normal force, I'll know the kinetic friction, obviously. So I'm going to set up a Newton's second law in the y direction, okay, just to figure out what the magnitude of the normal force is. And you can see it's down here, and this number actually makes a ton of sense. Normal force is basically the weight of the object minus the support by the tension. The support's pulling up a little bit, so it kind of lessens the effective weight of this thing. So this expression looks good, makes sense. All right, so our work is F delta R cosine theta, so that's what we got to do for these 4 forces. The displacement is directly to the right, so the work done by the normal force and gravity is 0. Okay, mathematically, it's 0 because we have a cosine 90 degrees, and cosine 90 degrees is 0. Conceptually, what's going on here is neither of these 2 forces contribute to increase in the speed or decrease in the speed of the baby brother. So it's, conceptually that's the way you can think about it. Should the normal force somehow speed the brother up or slow it down? Definitely not. Obviously, the only things that are going to happen here are the horizontal components of forces. So we have our work for tension. That's a positive work because it's pointing to the right. We're moving to the right. Magnitude's 30, displacement's 3, cosine 30 degrees is the angle between the 2 vectors. We got about 78 joules, right? And what's up with friction here? Well, it's going to be negative work. So I'm going to manually put the negative sign in there. The magnitude of kinetic friction force is mu sub kn. I know my n, it's down over here. Cosine is 0, again, because those vectors are effectively parallel, anti-parallel, but still. So I've got to put all my numbers in here, right? And I get about a negative 50 joules, So if I add up all those numbers, all 4 of those numbers, add them all up, I end up with a positive net work, right? So that means I know that the combination of all these forces will result in increasing the kinetic energy of what exactly is being pulled here? The Paul's speed. Okay, Paul's speed. So we're figuring out we know that Paul's kinetic energy increases by about 28 joules. Paul started at rest, so we'll set that equal to delta K. So the initial kinetic energy is going to be 0, and then obviously we're just going to find our final kinetic energy. So the final kinetic energy is this 28.14. We set equal 1/2 mv squared. Do your magic, solve for v, you get 2.4 meters per second. Right? Straightforward. All I got to do, look at the consistency in all these problems we're doing. We're doing the same thing. Free body diagram, write out the expressions for work, add them up, set it equal to delta K. Now, one thing I will say, though, we should be careful about this, is the third example where we happen to start at rest. Okay, so you can't just always set net work to 1/2 mv squared. That only makes sense because your initial kinetic energy was 0. But if you are already moving, you have to include another 1/2 mv squared, right? Because this kf is a 1/2 mv final squared, and this k initial is a 1/2 mv initial squared. So just be mindful of that. Okay, I think I might have an example. I do that anyway. Okay, so so we're now at the tail end of chapter 6 here, and there's sort of a miscellaneous topic that is involved with the concept of energy, and it's sort of relevant in this chapter because it very closely involved forces, but it's the idea of power. Now, here's the thing. One of the nice things about doing energy problems is this, that we don't usually have to invoke time. We solve energy problems, we're looking at basically two snapshots in time, and we're trying to characterize how the system looks, and then we try to sort of work out what's going on in the system. But when those two snapshots take place is not necessarily important. I mean, we don't actually need to plug in time anywhere. But there is a concept of time, obviously, in any of these problems, so that's what power attempts to discuss. And what power is basically the rate at which the energy is delivered. Okay, so for example, if you have that problem with the skiers being pulled up the incline by the rope, that's going to result in, positive work being done to increase the potential energy of the system. But exactly how that is delivered, does make a difference. I mean, if you can deliver, all that work in a matter of seconds, it's a huge, amount of power. But if you do it over the course of, say, a minute instead, I mean, so those characterize really different things. And so that's why power is very important, because we want to understand the rate, right? The rate at which the stuff happens. So, all right, let's look. Oh, wait. So anyway, the definition of this, and that's what the triple equality is, the top there. The triple equality means it's the definition. So the definition of power is the rate of change of energy over time of the system. And we do have a special unit for this. Okay, the units for this would be joules per second, which we call a watt. Okay, now there's this other archaic unit you might see occasionally, so I have to tell you about it. It's the English unit of power, which is the horsepower, even though we really haven't used horses for anything in for doing work. But anyway, it's still around. So anyway, it's a horsepower is 746 watts if you need to convert. All right. Not too common, but it's just something you might see. So here's some examples of power here. Our light bulb, if it's rated at 100 watts, what that means is it emits 100 joules of energy per second. Okay, so what's going on with this light bulb here is you got some filament in here. Tungsten's usually how these things are made. And it heats up to a large extent, and then it produces a lot of thermal radiation. Most of it's thermal radiation, and that's where the 100 joules per second are coming from. But that's actually normally it's a huge waste of energy here, actually, because most of that is put into like infrared light or put into heat or something like that, and it actually is a huge waste of energy. But that's a different story. Our athlete is a half a horse apparently here, and that means they do 350 joules per second of power here. So, one of the things that is useful for is to actually determine what the metabolic rate of the person is as they're performing this activity. You can convert those joules into a calorie, then convert them into a kilocalorie, because that's what food calories are measured in, and you actually can determine for this activity what's the caloric requirements for the activity. So that's actually something we get into in Physics 211, so if you have to go that far, it's involved in thermodynamics, so it's kind of a neat thing there. All right, you'll see also on the right here the gas furnace. The only thing I want to point out about the gas furnace is that for devices that require a lot of energy, that's usually expressed in kilowatts. That's thousands of a watt, and you've probably heard kilowatts because that's how it's a type of unit of energy, a kilowatt hour. So if a kilowatt of energy was used for a course over the course of an hour, that would be communicating what the energy usage was. And so that's actually how they bill homes for their, or businesses or whatever, for the use of energy. It's usually done in a kilowatt hour, and there's a rate for that, something like that. Usually it's like a quarter, or I don't know, 35 cents or something like that. All right, now there is another way that we can characterize power here, actually. And if we think about the original definition of power being delta E over delta T, well, if the energy that's changing is the result of work being done, okay, like through a force, then the delta E is really a delta W, right? And then if you look at delta W, dW dt, well, what's the work? Work is force times distance. Well, if you have a constant force, you can take the force out of the derivative, and then it ends up being dx dt, which is velocity. So an equivalent expression, depending on the circumstances, depending on what you have to work with in your problem, you could state that the power is done by the dot product of force and velocity. This does require, however, that your force is constant over the displacement. Otherwise, you can't pull the force out of that derivative. And while you could still set this problem up in that way, it's going to be a little trickier because you're going to have, like a chain rule thing going on with your derivative. We don't, if you have anything like that, you just go back to the original definition. You don't want to get messed up with the mathematics here. Anyway, evaluating that dot product. So just in terms of magnitude, it would be FV cosine theta. Okay, so quick check here for these students. We want to try to determine what is the largest energy output of these things. Okay, so we want to think about this a bit. Now, as you're thinking about this, let me talk a little bit about what you ought to be thinking about here. So the definition that we want to be using here, we don't want to use the force times velocity definition because we don't really have any information about velocity per se here. We have a better sense of a dE, delta E over delta T. So there's a change in energy that occurs over a period of time. That's the key here. And then what the change in energy is an increase in potential energy. So for each one of these students, you can characterize their increase in potential energy, right? You have their mass times 9.8 times the height that they go up the stairs. It's not the distance they travel, it's just the height that they go up, because that characterizes the change in potential energy. So you can work that out for all of these things. You can work out mass, g, height, divide that by delta t, and what you will find here is that the answer is B. So what's happening here is we have, the most amount of mass going up the steps at a faster rate. Okay, so you can see that B is more power than A because you're going the same length faster, right? You're going up the same height faster, so that's more power. We could tell that we're better than C because we have more mass in the same amount of time. So that requires more energy to make a greater mass go up the stairs. Okay, if we go to D, what's different about D? Well, we have to go up twice the height. Well, if we did it at the same rate, the time should be 16 seconds. So doing 25 seconds means we're slower. That means our power output will be less. So the answer here will be B. Okay. All right. I think I have a couple more examples here. I do. Let's get through these last two examples here. Okay, so we want to know which consumes more energy, a 1.2 kilowatt hair dryer used for 10 minutes or a 10 watt night light left on for 24 hours. Okay, so we want to use our delta E over delta T definition for power. We're solving for delta E. The hair dryer is 1200 watts operating for 10 minutes. So we're going to put that in seconds. So we have the units of joules. And we get 720,000 joules in the 10 minutes of time. The night light, being that it is 10 watts, is left on all day. So the day has 86,400 seconds. And so we multiply that, we get a slightly larger amount of energy. Okay, and so what this is trying to illustrate here is that, over the course of the day, your nightlight is actually using more power than the hair dryer, although I think this better demonstrates that the hair dryer is just kind of a big energy hog. Same thing with like vacuums. Vacuums are usually pull a lot of power, things like that. So, honestly, if you're trying to save energy here, hair dry, use your hair dryer for 5 minutes instead of 10 minutes or something like that. Or just don't be afraid of the dark. How about that? And then no night light. Anyway. Okay. Okay, last problem here. And this is a great problem because it kind of incorporates everything we've talked about up to this point, like everything in this chapter. So this is a fantastic way to finish this here. We got an 8-gram bullet with a speed of 800 meters per second is shot into a wood block and it penetrates 20 centimeters before it stops. We want to determine the average force of the wood on the bullet, and we want to determine the rate at which the wood takes energy from the bullet. All right, so if we want to know what the average force is, we are going to be using our work-kinetic energy theorem, but we're going to be working backwards from how we normally been doing it. Normally we figure out the work and then we figure out something about the motion. Well, we're going to do the opposite here. We already know the motion. We're trying to go back and figure out the amount of force that's being done. So I got a little bit of a free body diagram on the right here. It's not a complete free body diagram because I didn't include gravity and I don't include like a normal force or anything like that. But it's an 8-gram bullet. It's not very massive and it doesn't really contribute to the work anyway. So I just decided not to put it in there. So we just got to force this backwards. The bullet's going to the right. All right, so there's only really one force to consider here. The wood is doing negative work because you're reducing the kinetic energy of the system. So it's a negative F delta X. We know our delta X is 20 centimeters. Make sure you put that in meters though, 0.2 meters. That equals delta K. The final kinetic energy is 0. We come to a stop. We have initial kinetic energy. So we have a negative 1/2 mv initial squared. We can solve for the force here. I have that expression down here. We put in all those numbers and we get 12,800 newtons. So that was the average force. Okay, that may not be exactly how the force was applied, but was it applied equally over the course of those 20 centimeters? Probably not, but all we can really say here is an average. Again, if we had some means to know what the variable force was, then yeah, we can get a more detailed picture. But for now, this is just an average. All right, we have to determine power. Okay, so the delta E over delta T is what we want here. We don't want to use the FV thing. We don't really know anything about. Well, the force is probably not variable, and the speed is definitely not. Sorry, the force is not constant, and the speed is definitely not constant. I mean, you really need the force and the velocity to be constant to really do that stuff there. So the FV is usually useful if you're pushing something at a constant speed, and then you can determine what power is being done there. Anyway, so we have our delta E. It's the change in the kinetic energy, which is the 1/2 mv squared, and the delta T is how long this took. So we do need to work out a kinematic problem because we have to know how long the interaction took place for it. So I've done the kinematics on the right there. I used equation 3 to figure out what the acceleration is, right? And that's the first line there. And then below that, I've done equation 1 to then take that acceleration with the velocities and work out a time. And so what I get here is a 1/2 millisecond. So that's how long it took for the bullet to be embedded in the wood. So I'm using the 5 times 10 to the minus 4 in my expression for power. So I end up with 5.1 times 10 to the 6 watts. So, it seems like a ton of power, right? It's a 5 megawatts, right? But it's applied in 1/2 millisecond, so that's okay. Okay, you can make a megawatt generator apparently if you can just have a machine gun just into a block of wood. But you probably run out of bullets before you get anywhere with that. Okay, so we are done with this chapter here. And the next chapter, we're going to be getting into the conservation of energy. So we're going to be talking less about work and getting more into dealing with energy states. And we're going to be looking at potential energies a lot more as a result of that. Okay, so thanks for listening.